Today we want to look at rate of change. Calculus is about studying how functions change. Calculus is about studying how things are changing. Calculus is about studying the relationship between a quantity and how that quantity is changing. We usually frame this with changing over time because this is calculus. This is pretty much an engineering class, which means it's just kind of in support of physics. It's less a math class and more of a physics class by way of engineering class. It's math for engineers. I know when I say it like that, it kind of means that I feel like you engineers might feel like I'm looking down at you because I'm like, oh, I'm a mathematician. It's like, oh, it's math for engineers. Like the way I say it like that. And I only want you to know that it sounds that way because I kind of mean it that way. I'm just kidding. I'm totally kidding. Because in the hierarchy of people that get to go into the shelter during the apocalypse, I am not on that list. Right? I recognize that I'm not on that list. I'm a mathematician. It's like, well, we got an extra space. Right? Have you been on a diet? It's like, oh yeah, I'm kind of not eating as much. Okay, then that's useful. That's useful. You can come on in. Then an engineer is going to show up. It's like, oh, excuse me, I'm an electrical engineer, and then I am right out. And the electrical engineer is like, oh, ha, see you later, leech. I can actually know stuff that's useful. And then someone's going to tap that guy on the shoulder and says, I am an electrician. And then the electrical engineer is out because the electrician can actually do the stuff that's actually being worked on, right? So anyway, what are we talking about? I'm just kidding. So calculus is about studying how things are changing, looking at the relationship between a function and how that function changes. So there are some well-known functions where we understand how they change. Yesterday, we talked about exponential functions. Exponential functions change via multiplication. That's how they are changing. Some other ones that are famous that we know about, linear functions have a constant rate of change. Linear functions have a constant rate of change. Linear functions are our favorite functions because of this constant rate of change. This is our default mode of thinking. Thinking linearly is the default mode of thinking. You're always thinking constant rate of change. If we're bargaining and you're at 5,000 and I'm at 3,000 and we decide to split the difference, where do we land? At 4,000, that's splitting the difference. It's making a linear function between 3,000 and 5,000 and going halfway in between. Our default mode of thinking is linear. And we represent, so the operation that's going on behind a linear function is addition. Linear functions are just repeated addition. That's what makes this constant rate of change. Linear functions are repeated addition. Repeated addition. Linear functions are the model that we create when we see repeated addition. Add the same thing over and over again. This is our favorites. I know you all might have heard of this as mx plus b. That's like super backwards. It's b plus mx. That is a better way of writing it. Fight me. I'm just kidding. You'll lose. B plus mx. This is a better way of writing it because this is how we should think about linear functions. Start at b and add m a bunch of times. That's what this is saying. That's the way we think about this equation. We need to tie those two things together. Too often those things are separate. I can tell they're separate because I have students in algebra classes writing down the slope formula, claiming to understand the slope. If you have to write down the slope formula, you don't understand slope. You should not have to write down the slope formula If you did, someone has done you dirty as far as teaching you what slope represents. But that's what this equation says. This equation says y is b when x is 0, and we're going to add m a bunch of times. X is just a standing there for a bunch of times. So this says y is b when m is 0. I'm going to use green for go. That's where it starts. Oh, sorry, when x is 0. And then the next thing it says is plus m, add m times x a bunch of times. This plus m is add m a bunch of times. That's the times x. We add m x number of times. This is how we read a linear function. This is a constant rate of change. It's repeated addition. Start with b and add m a bunch of times. When x is 0, y is 10. And when x increases by 1, we add 3 one time. When x increases by 2, we add 3 a second time. When x increases by 3, we add 3 a third time. Start at 10. Add 3 a bunch of times. That plus 3, plus 3, plus 3, that repeated addition, that's the constant rate of change. We're describing how the function changes with a constant. The change is how much are we adding? We're adding 3. There's our constant rate of change. We usually summarize with b plus mx, where m is the unit rate of change, the rise divided by the run. Kind of a terrible way to do things, but I mean, we're too far in now. Slope is just going to have to be rise over run. But for a slightly better way to think about it, that's more workable. If you split the run over under the x, now we add the rise every run units. Start with b, add the rise every run units. This is, of course, not how we would write this. We would not want to write y equals, I'm going to do a different one, 7 minus 2/3 x. That's not, we would write it this way. We would write the 2/3 as the slope. That's going to be the coefficient. Y starts off at 7 and decreases by 2/3 every 1 unit. That's how we would read that. But if we wanted to make a table with integers, since we have a rise of -2 and a run of 3, we could say y starts at 7 and decreases by 2 every 3 units. We could put this read on it. Because when we take x and divide it by the run, now we're just counting the number of times we're going to subtract 2. So y is 7 and decreases by 2 every 3 units. Sorry, y is 7 when x is 0. And y decreases by 2 every 3 units. So if we're going to make a table of values and we don't want to have like fractions because y'all are fraction haters. Everybody hates on fractions. I don't know why. There's got to be like all number racists. But we'll start y at 7 and we'll decrease by 2 every 3 units. Decrease by 2 every 3 units. Decrease by 2 every, every 3 units. I switched them. Decrease by 2 every 3 units. Decrease by 2 every 3 units. This is going to be the same table as decreasing by 2/3 every 1 unit. But it's all integer focused, so I don't trouble students by writing fractions. Yes. 3 minus 2 is, look, an eagle. I don't know what you're talking about. I wrote +1, so it's +1 right there. I was wrong about that. Thank you. Any questions? Comments? I'm not very good at arithmetic. Once you see me start doing arithmetic, watch carefully. I don't know if that's going to work out. The reason that I like this construction, not to be the way, this is not the way we are going to do this problem. That's not how we would write things. This is how we think things, is that this showed up yesterday. This showed up yesterday when we started talking about exponential functions. Exponential functions are also another well-understood function for us. We know that exponential functions are changing through multiplication. And the way we would describe that in terms of rate of change, we could say exponential functions have a proportional rate of change. Exponential functions have a proportional rate of change. A lot of times we use population to represent exponential functions. And that if we double the size of the population, then the population can increase. Its rate of change will be twice as much. We not only double if we double the population, we have doubled the rate of change. The operation, like we saw yesterday for exponential functions, is that exponential functions are for repeated multiplication. Oh, now that that's come up. In linear functions are for repeated addition. We use multiplication to represent repeated addition, and here's that multiplication. Here is our repeated addition. Multiplication is repeated addition. There's the multiplication, m times x. Exponents are for repeated multiplication. So we would have m to the x, because that would indicate repeated multiplication. exponential functions are for repeated multiplication. And in that way, we can use the same kind of construction that we have for linear functions, just replace repeated addition with repeated multiplication. So when we write the generic exponential function a times b to the x, this is the b plus mx of exponential functions. We would say that y is b when x is 0, or sorry, y is a when x is 0. That is, starts at a. And now instead of just stating how much increase we have, how much we're adding, we're using a different operation. We're going to multiply by b. That's the next thing we say in the equation anyway. Multiply by b. A bunch of times. The exponent says how many times you multiply by b. X will be the number of times we multiply by b, because that exponent is telling you how much repeated multiplication to do. So if I just modify my previous example, starting at 10 and changing with a 3, instead of adding 3 every unit, I'm going to multiply by 3 every unit. So we'll multiply by 3 in 1 unit, then the next unit we'll multiply by 3 again, and then we'll multiply by 3 again, and then we'll multiply by 3 again. Yes. I multiply by 30. Thank you. It's funny because when I'm writing stuff, like the part of my brain, so that's not right. But I'm like, when I'm writing, my hand is like, all, now we're writing now, bro. My God. And then like, he's like, are you going to tell him? I don't know. Are you going to tell him? One of the students will tell him. Yeah, all right. What we got? 10 times 3 is 30, times 3 is only 90, right? I started putting a 10 over here with the 3. So I was like 1 times 30 to the x. 3 times 9 is 27, but only 1 0, right? And then 81 with 1 0. All right, there we go. I should just put a 0 in. What we're doing is we're multiplying by 3. Now that we've got it right, we're multiplying by 3 every 1 unit. This is where we find out why I like the splitting the run to under the x like we had before. The reason that we can get away with rise over run is that we're using multiplication. Rise divided by run and multiply by x, that's all multiplication. I know there's some division in there, but it's the same shit. It's all multiplication. It's all on the same level. So I can say, if I have the rise divided by the run times x, that's the same as taking x divided by the run and multiplying by the rise. Or I could take the rise times x and then divide by the run, but I mean, no one would do that. No sane person would do that. That's actually how I find out who is the robot in the class. Like in every class, there's a robot sent from the future to murder me and to find out who they are. I just watch them do rise over run times x. If they're like, well, we multiply the rise times x and then divide by the run, and then they write down, and we come up with this answer. Then they look up, and that's when I have my phase plasma rifle with the 40-watt range. I knew it was you all along. I know I said rifle, and I was holding it in one hand. I don't know if you've had a phase plasma rifle in the 40-watt range. They're one-handed. I mean, they've got like the butt and everything, but they're one-handed. So. All right. Has everybody seen Terminator? All right. So the reason that I like the x over run is if we're going to not multiply, let's say we're not multiplied by 3 every 1 unit, but we're going to multiply by, oh, I'll change that up there. It doesn't matter. If we're going to multiply by 3 every 2 units, or if we're going to multiply by 2 every 3 units, to copy the one from above. So if I want to describe a scenario where y is equal to 7 when x is equal to 0, and I want y to be multiplied by 2, but not every 1 unit. I want to stretch it out and make it take 3 units. Then I can write the function y is equal to 7. I'm going to multiply by 2, but the exponent is going to count the number of times I multiply by 2. So the exponent is where we're going to be dividing by 3. So now the exponent is 0 when x is 0. The exponent becomes 1 when x is 3, because when x is 3, that's when we should have multiplied by 2 1 time. When x is 6, we'll have multiplied by 2 2 times. We're still doing, we're multiplying by 2, so 14, 28, 56. I know it shouldn't be taking me this long to multiply by 2. This is why I switched from 3 to 2, so I could actually maybe successfully perform the multiplication. Now I got to switch to addition. We're doing this every 3 units. Now, if we want to multiply by 2 every 3 units, we can figure out what's going on every 1 unit. In a linear function, all we have to do is take the rise and the run and just like divide the rise by the run, because everything's going through multiplication. But here, not so much. That over the run part, the over 3, is part of the exponent. And that's why when we rearrange this, we're taking 7 and we're multiplying by 2 to the 1/3 power, and then that's what gets raised to the x. So the unit multiplier is going to be 2 to the 1/3. We can't just divide by 3. That's linear functions because we have repeated addition. But now that dividing by 3 part is part of the exponent. So I need to know what the cube root of 2 is. Hey Siri, what's the cube root of 2? Thank you, Siri.
Welcome.
This comes up on one of the homework problems because the homework problem says, write a possible formula for this exponential function. And then I think it's picked out 1. So it's kind of a dick move on that part, on their part. But there are an uncountable infinity of possible answers. But there are only a couple that actually make sense. So multiplying by 2 every 3 units is the same as multiplying by 1.2599 every 1 unit. Any questions? We can also interpret this other ways. Yesterday, we saw that exponential functions are when things are increasing by percent. So if you have some function that is increasing by 25.99% per unit, you know that it will double in 3 units. Any questions? Comments? There's not really a good rule for it. Right now, everything is just, it's just wherever I say you should. Usually I'll say 3 significant figures. So we would probably go with 1.26 at this point. But in some applications, I might say 5 significant figures. If we're going to use this function, then we might not want to do any rounding. The more we round, the more error we introduce. As far as what we write down, we would probably write down, I would probably just have you write down 1.26 to the x. But the farther out we go, the more that this rounding is going to work against us. It's not that far off because apparently it was 1.2599. So 2 to the 1/3 power is 1.25992105. So if I use this function, 7 times 2 to the 25 divided by 3. Let's see how far off we'll be if I use 1.26 to the 25. Not that far off, or are we that far off? Is this a big difference? It depends. It depends on a lot of things, right? So, if there's going to be a problem where you're rounding stuff off, I will always specify where you need to round off. If I don't specify where you should round your answer, and you're getting an irrational number, I might be expecting an integer. So double check your word. It's very suspicious because I'm like, oh, here, just write the answer. Just type the answer. Just type the answer. Round your answer to 3 significant figures. Like, oh, now I'm suspicious. So the unfortunate answer is it depends where to round it to. How's everybody? Okay? Everybody looks so happy. You all look like this. But I get it. I don't know if you have looked outside, but it's like sunny outside. It's sunny outside. What a lovely day to be stuck in a classroom, listening to some Yahoo yammer on about that. And to be stuck here, right? Because look where the doors are. And look how I'm conducting the class. I'm facing you the whole time. Like if I was working on the board, I'm like, all right, let's do another problem. And then I would be like turning my back and you just like, oh, so like ninja your way out the classroom, right? You just like subtly get your stuff packed up. Then I turn around. He's like, all right, the next problem that we're going to work on is, and you're like, there you go. You don't have to do that, by the way. You need to go. Just go ahead and go. You should be quiet, yes. But you don't have to sneak out. It's not like I'm going to stop you. You know what I mean? I worry about the things that have happened to you with previous instructors that you're worried that I'm going to stop you as you're trying to leave the classroom and quiz you on what you need. Like, I don't need to know your business. I don't even want to know your business. Because a lot of times we'll be taking a test or some shit and people are like, can I go to the bathroom? Like, what am I gonna say? No. No, sit down. I want you more uncomfortable for the test. Thank you for letting me know. You don't have to ask. Sometimes it's like during a test or something like that. You just, maybe you just want to go out and have a cigarette. I don't know. You shouldn't smoke, but I mean, I'm not going to judge. I mean, yeah. It's like, oh, I need to go out, or maybe you just need to go outside because it's sunny. They're like, oh, this is skyline. That can turn bad real fast. It could just like the fog could be like right on the other side of the building waiting for us. There's a fog on the other side of the building. Hold, hold. And then Leach says, I'll see you next week. And it's like, oh, no. And you're like, oh, yeah, I'm going to go enjoy the sun. And all of a sudden, fog. And Pacifica and San Bruno just high-five each other. Got him. And then you start feeling persecuted by the weather. You know what I mean? I don't mind the fog, just personally. There's a reason I teach at Skyline and not CSM or Kenyatta. I mean, Kenyatta is super nice. I don't know if you've been to Kenyatta. The campus is like super nice, and they got like these beautiful views. Like, because it's up on one hill, there's a highway, but the highway is down here. Kenyatta's like, oh, no. We don't want to see the highway. Put us above the highway. Oh, thank you. And then let's look out onto the hill. Yeah, lovely. But it's just too hot down there. Yeah. Anyway, what are we talking about? Exponential functions are repeated multiplication. That's why they're exponential functions. It's repeated multiplication. And their rate of change is proportional. So notice the rate of change is proportional. So here we're multiplying by 2 this whole time, right? Times 2, times 2, times 2, times 2. But if we look at the rate of change, just how much we're adding, when you think of rate of change, how much we added. Our rate of change, the amount that we've added, that's not purple, red will work. From 7 to 14, we've increased by 7. From 14 to 28, we've increased by 14. From 28 to 56, we've increased by 28. 28, spelled 8 wrong. And then from 56 to 112, we increased by 56. So the amount of increase is doubling as the function doubles. The rate of change is proportional to the value of the function. That is, when there's twice as much function, the increase is twice as much. Twice as much function, double the function. Twice as much function, twice as much increase. A double-sized population will be growing twice as fast. When your investment has doubled, it is growing twice as fast as it was when you started out. That might still be slow. I don't know. So in an exponential function, the rate of change is proportional to the function. Any questions? Comments? Slide remark. I know this might be going backwards. This might be a different take on exponential functions than you may have seen. That's why I wanted to talk about exponential functions. We all come from different backgrounds as far as exponential functions go, as far as math in general goes, but it's exponential functions especially. And it's especially frightening our lack of focus on exponential functions, considering how much we allow exponential functions to run our lives. Our lives are run by exponential functions. Stuff increases by percentages. Your interest rate is some kind of percentage. all these exponential functions running our lives, and a lot of people don't even know what the base of the natural logarithm is. It's almost like we don't want you to know things. Ah, shit, they heard me. All right, I've got to go. This has happened before. I'm just kidding. All right. They have a terrible response time, so I'm not. Plus, I'm not very influential. I mean, no one listens to me. It's like, oh, he has some strange ideas, eh? What does he do? He's a math teacher. Oh, so no one listens to him. Yes, we're perfectly safe. All right. Quadratic functions have a linear rate of change. Quadratic functions have a linear rate of change. It's too late in the day to do any kind of fancy quadratic function, so I'm just going to go with the most basic quadratic function. Y equals x squared. Notice that the amount of increase we see here from 0 to 1, there's an increase of 1. From 1 to 4, there's an increase of 3. So our rate of change is not constant. But the rate of change of the rate of change is constant, and that means that the rate of change of the function is linear. So here, the rate of change of the quadratic is linear. Because one level down from this, from 1 to 3, the rate of change is increased by 2, from 3 to 5, from 5 to 7, and from 7 to 9. The rate of change of the quadratic is linear. The rate of change of that rate of change is constant. Because that's what a linear function has, a constant rate of change. For those of you with a secret mathematical knowledge of derivatives, yes, this is just the second derivative. When we say rate of change, we're going to be talking about derivative. When we say the rate of change of the rate of change, that's just the second derivative. So in case you were wondering, if you don't know what a derivative is in the mathematical context, that's okay. It's what this class is about. You'll get this. I just didn't want that tension over the whole weekend. It's like, oh, was he talking about derivatives? I think he was talking about derivatives. Not like the financial thing with derivatives. I don't know anything about that. So we want to be studying how functions change. And one of the things that we're going to be looking at is the rate of change of a function. And we can see how all these functions change. Now we could also, no time to graph. We could also look at the graphs. We know that a constant rate of change will make a linear function, so that it's going to just a flat change. We know that when we have a quadratic function, we get a parabola, so it bends up. We also know that exponential functions start to grow very fast. Eventually, they'll be growing very fast. A lot of times we like to say something is growing exponentially when we mean it's growing fast. The reason that people do this is that you sound like a fancy person when you're like, oh, it's growing exponentially. Every time someone says exponentially when they mean fast, just ask them, oh, great, what's the multiplier? They'll be like, oh, what? You said it's growing exponentially. What is the multiplier? How long is it going to take to double? And what data do you have that shows that that's consistent? Well, I just meant it's growing fast. Then just say fast. You know what I mean? But anyway, there are certain things I'm going to plant the flag. I've already given up on beg the question. Beg the question now means raises the question. It's very upsetting to me, but I've had to let it go. That's just the way language is. Language changes. Like literally me is just an emphasis now. Literally is used for emphasis. If everybody does it in the language, then it's correct. I'm very sorry to say. Because some people that are like, oh, you can't use literally that way. I'm like, well, explain to me the difference between who and whom. They're like, oh, whom? Why would you put an M on the end of who? See, language evolves, it changes. Stuff means different shit over time. This is the way it is. And I've had to give up on begging the question. But this I'm not letting go. Exponentially means specifically growing by multiplication. There's some multiplier, you can identify how long it's going to take to double. If you want to say it's growing fast, let's say it's growing fast. That's cool. If you want to emphasize that, it's very fast. Because exponential functions don't actually always just grow fast. If you've got an account that's increasing by 0.5% every year, it's not growing fast. It's growing exponentially, but it's not growing fast. Like, oh, at the end of the year, I'll have that extra ½ cent. It's growing exponentially. You know what I mean? It's like, oh, knock it off. Just use the words. That's why we have them. This is, I think, why I like math. Because math doesn't really change what its words are. We'll like get rid of some shit, like we don't have coordinate and abscissa anymore. We just say x coordinate and y coordinate. I don't even know which one is which. We just say x coordinate, y coordinate, the language evolved, and we just got rid of stuff. We didn't like introduce something new and worse. And we didn't try to make ourselves sound. All right, that's going to do it for today. That's going to do it for this week. This afternoon, I'm going to be sending out some authorization codes. So check your email for that. Other than that, that's it. Email this to you, Grandma. I'll see y'all on Monday. Everybody have a good weekend. And thanks for playing.